Okay. In the last class, we discussed about right hand limit and the left hand limit of a function. So for finite number, so that means what? If x goes to a finite number, then f of x goes to finite number. Now, what is the definition of limit of a function at infinite points? That is, what is the limit x goes to infinity f of x? So, but in the last two class, we discussed about limit x goes to a f of x exists, we call this here. So there are two cases, right? If a is finite number, L is finite number, we discussed. Now if say either a is infinite or L is infinite, what the definition of this one? And what is the definition of this actually? If you take any epsilon greater than 0, there exists a delta greater than 0 such that whenever modulus of x minus a 0 strictly less than x minus a is less than delta implies modulus of f of x minus L is less than epsilon. So that is the definition of limit x goes to a f of x equal to f. Now we discuss about limit at the infinite and the infinite limit. Suppose when we say, or simply saying that if x approaches to a implies f of x approaches to a, then we say L is the limit of a function at a point A. Now, first definition, now we discuss about infinite point. First definition, a function is said to have limit L as x goes to infinity. So that is, when we say f of x approaches to L as x goes to infinity. Okay. What is the definition? Again, for every epsilon greater than 0, there exists a positive number n in n such that the modulus of f of x minus L is less than epsilon whenever x is greater than n. Okay, or if we take k means greater than k. Okay, whenever x greater than k, then f of x and then Ls are very close. Now this is because here one limit is infinite, but this L is finite. Now similarly we define for x goes to minus infinity also, right? So what is the definition of that one? So when we say f of x approaches to L as x approaches to minus infinity. The same thing for every epsilon greater than 0, there is a positive number k in n such that the distance between f of x and L is less than epsilon whenever x is less than minus k. That is, x is very near to infinity. I put minus k. Now we take this L is infinite, A is finite. X goes to finite number. What is the definition of this? That is, third definition. Suppose f of x approaches to infinity, but x approaches to E as x approaches to E. So what is the definition? Again, there is a positive number, maybe is anything. Okay. So given any k greater than 0, there is a positive, there is a delta greater than 0, such that f of x is strictly greater than k whenever 0 less than modulus of x minus a is less than delta. Okay. Now similarly, if f, what is the definition of f of x approaches to minus infinity, x goes to a. So f of x approaches to minus infinity as x approaches to some finite value. So again, given any k greater than 0, there is a delta greater than 0 such that f of x is less than minus k as 0 is strictly less than x minus a, strictly less than delta. Now suppose both the limits are finite. So similarly we can define all the possible cases. Okay. So next definition, when we say f of x approaches to infinity as x approaches to infinity. So simply saying what is the limit x goes to infinity f of x. So what is the definition again? So again, for if you take any given greater than 0, and there is a positive number m in n such that f of x is greater than k whenever this x is greater than m, because both f of x and the x are very near to infinity. Okay. Similarly, if you take similar, we can extend to minus. Suppose when we say f of x approaches to minus infinity as x approaches to, suppose okay, this okay, suppose we take plus infinity and this is minus infinity, and same thing, but x should be, you can take less than minus m. So similarly, we define for minus infinity plus infinity all the possible cases. Okay, same definition. This is actually minus m. Suppose if you take this plus infinity, f of x approaches to infinity as x goes to infinity is again given any epsilon greater than 0. There is a positive number m in n such that whenever, so f of x is greater than k whenever x is less than minus m. Because x is very close to minus infinity, that's why I'm putting x is less than minus m. Since f of x is very close to infinity, that's why I'm taking f of x greater than k. Okay, so similarly, suppose f of x approaches to minus infinity as x goes to infinity. So again, given any epsilon greater than 0, that is given any positive k, and there is a m positive number such that f of x is less than minus k whenever x is bigger than m. Suppose both are minus, that is f of x approaches to minus infinity as x approaches to minus infinity, means what? Given any k greater than 0, there is a positive number k m greater than 0 such that f of x is less than minus k whenever x is less than minus m. Okay. So these are definitions of limit of a function at f at infinity. Okay. Now we discuss some examples. Okay, yeah, no need to do that. Anyway, we already found that. Okay. Now, when we say the function does not have a limit exists at the point, so we know that limit exists means what? If you take any sequence xn converges to a, then f of xn converges to f of a, then we say the limit exists at a point. Okay. But when we say the limit does not exist, if you take any two different sequence xn converges to a, but f of xn does not converge to same point. Okay. So we discussed some example to that. So already the yesterday class I mentioned that limit x goes to 0, sine of 1 by x, the limit does not exist. But if you multiply with the x, the value is 0. Okay. Now today we are going to discuss why the limit x goes to 0, sine 1 by x does not exist. Why? Does not exist. So therefore, if we take any two different sequence xn converges to 0, but f of xn does not converge to the same point. That is, we are going to construct two sequence xn, another sequence xn dash, both are converges to a. What is the definition? If you take any sequence converges to a, f of xn converges to f of f of xn converges to l. If suppose l is the limit. Okay. So here a is 0. Therefore, if you take any sequence xn, but all the xn's are non-zero, but converges to 0. Again, suppose if you take some other sequence xn dash converges to 0, the both the f of xn and the f of xn dash converges to the same limit. If this is happened, then we say limit is exists. Suppose this f of xn converges to some L1, this f of xn dash converges to some L2, but L1 not equal to L2, then the limit does not exist. Okay. Now we can produce some sequences, two sequence xn dash, both are converges to 0, but f of xn dash converges different points. Okay. So choose xn equal to 1 by 2n pi. Anyway, all the xn's are non-zero, but this converges to what? 0, because 1 by n. 2 pi is a constant. Anyway, 1 by n converges to 0. Now, what is our function f of x? F of x equal to sine of 1 by x. That is our function. Now, what is f of xn? Sine of 1 by xn. But what is xn? 1 by 2n pi. Therefore, 1 by 1 by is nothing but sine of 2n pi. Sine n pi is always 0. Okay, therefore, this is nothing but 0 sequence. This 0, 0, 0 is converges to 0. Now, we are going to choose another sequence xn dash equal to 1 by 2n pi plus pi by 2. So, what about this? This also converges to 0. Yes, 1 by n is there, right? Therefore, this converges to 0. Now, what is f of xn dash? It's nothing but sine of 2n pi plus pi by 2. If I apply sine a plus b, sine a, sine b, sine a cos b plus cos a sine b, you'll get 1. So this is a constant sequence 1, 1 is converges to 1. Now we have a different limit. Therefore, the limit does not exist. Limit x goes to 0, sine of 1 by x does not exist. So suppose you want to prove the limit does not exist, you have to find a two sequence x and dash converges to same point, but f of x and dash converges at different points. Okay. Now, I mentioned that the continuity. Suppose the limit exists and the limit is f of a, then we say f is continuous, right? So limit x goes to a, f of x equal to, suppose f is defined on a and we will get f of a, then f is continuous at point a. Then actually if and only if f is continuous at a point a. Okay, this is a definition, another definition for continuous. Anyway, everything is equivalent. So now when we say the function is discontinuous, therefore there are types of discontinuous that are there. So what are the possible cases? Either the limit exists but not equal to f of a. If this has happened, then we say f is not continuous. This is one type of case. Sometimes the limit does not exist. That is also another possible case. Okay, there are two cases. Now we discuss what is a type of discontinuous. Okay, types of discontinuous. So the first type we call a removable discontinuity. So when we say a function is removable discontinuity at a point, removable discontinuity at a point some c. Okay, at c means what? So the limit exists but not equal to f of c. So that is, if when we say a function is removable discontinuity at a point c, if limit x goes to c, f of x exists but not equal to f of c, but not equal to f of c, then we say that discontinuous is called a removable discontinuity. Okay, so that is, limit exists but not equal to f of c. If equal to f of c, then we say it's a continuous. The limit exists but not equal to f of c, that this discontinuous is called a removable discontinuity. That is the first type. Now, the second one is discontinuous of first kind, and we call it a jump discontinuity. Okay, discontinuity ITY continuity of first kind. or sometimes called or jump discontinuity. So there is a jump discontinuity. So when we say a function is of discontinuity of first kind, if both the limit exist, that is the right hand limit, left hand limit exist, but not equal. So that is limit x goes to some, if we take c plus f of x, and this exists but not equal to limit x goes to the left hand mean f of x. Both the limits are equal but not equal to things. Such a discontinuity is called jump discontinuity. But in the previous one, both the right hand limit, left hand limit exist and both are equal, but that is not equal to f of c. But the right hand limit, left hand limits are equal, but not equal to f of c. But here, right hand limit, left hand limit exist, but not equal. That is discontinuity of first kind. Now, discontinuity of second kind is nothing but neither the right hand limit nor the left hand limit exist. Okay, or none of them exist, right hand limit or left hand limit. So, discontinuity of second kind. Okay, so when we say a function have a discontinuity second kind at the point, neither the left hand limit nor the right hand limit exist. Neither limit x goes to c plus f of x nor limit x goes to c minus f of x exist. Okay. If none of the limit exists, then we say the function is of discontinuity of second kind. Okay. And there are some more thing is there. So discontinuity of second kind from the left means what? The left hand limit does not exist, but the right hand limit exists. Okay. And then discontinuous second kind from the right means what? The right hand limit does not exist, but the left hand limit exists. If both the limits are does not exist, then we say simply say discontinuity of second kind. Okay. So when we say the discontinuous second kind from the left, that means what? The left hand limit not exist. Discontinuous second kind from the right means what? The right hand limit not exist, does not exist. Okay. And another thing is mixed discontinuity. Mixed. So mixed means what? Second kind, one of the side must be okay. First kind or maybe continuous. So the last one is mixed discontinuity. Mixed discontinuity. So a function is said to have mixed continuity at a point C if f have a discontinuity of second kind on one side. Okay, on the other side, discontinuity of first kind. Okay, so there are two sides, right hand side, left hand side. So at a point C, one side we have a discontinuity of second kind, another side is a discontinuity of second kind. Okay, that is we say it should be mixed discontinuities. Okay, anyway, now we discuss some example to check the function is continuous or not. So example.
Sir,
Yes.
sir, can you repeat this mixed discontinuity?
Yeah, mixed discontinuity is what? So, okay. Maybe I will, okay, I read a statement and then we will discuss some example to this. Okay, so when we say a function is mixed discontinuity at a point x equal to c, if f has a discontinuity of second kind for one side, that is one side means either right hand side or left hand side. Okay, so f has discontinuity as a discontinuity of second kind of the second kind on one side either right hand side or left hand side, one side of x equal to c. Okay. And the other side That is other side, a discontinuity of first kind. A discontinuity of first kind. Okay. Or may be continuous. We discuss some example to this. Okay. Example. Suppose if a function is defined to be f of x equal to 0 if x is less than or equal to 0. For all negative values, it takes 0. For all positive values, if x is strictly greater than 0, is sine of 1 by x. Now, we are going to discuss about a discontinuity of limit. Because we know that at the point x equal to, at the point limit x goes to 0, the function does not exist. Okay? Does not exist. If it is exist, then it is okay. If it is equal to f of 0, then it is continuous. But the limit does not exist. Then we have to, this is a discontinuous function. Then this function is discontinuous of what kind? Okay. Now, what is the left hand limit? What is the left hand limit? What is the limit x goes to 0 minus f of x? What is it? So that means what? If you take any sequence xn which is less than 0 and xn converges to 0, then what is f of xn? Right? What is f of xn?
0.
0. 0 sequence converges to 0. Therefore, the left hand limit is 0. But what is f of 0? From the function. Since x takes 0 here, therefore, this is nothing but f of 0 is 0. So, therefore, we get this is equal to f of 0. Okay. Now, therefore, f of x is continuous from the left, not continuous function, continuous from the left, because we get f of limit x goes to 0, 0 minus f of x goes to f of x, f of 0. Therefore, f of x is continuous from the left. F of x is continuous from the left. The limit exists and equal to f of 0, therefore, is continuous from the left at the point x equal to 0. Okay, therefore, this we got to find the right limit. So, what is the limit x goes to 0 plus f of x? So, that means what? If you take any sequence xn which is greater than 0 and xn converges to 0, then what is f of xn? So, xn's are positive, therefore, this is nothing but sine of 1 by xn. Now, again, already just now we proved that the limit, what happened limit? So, limit exists or not?
No.
Not exist.
So, therefore, we have a different limit. Okay, maybe if you take some other sequence xn converges to 0, we get 0 sometimes, we get a plus 1 sometimes, even you can take a minus something. Okay, therefore, this limit does not exist. So, limit does not exist, therefore, f of x is discontinuous of the second kind from the right. Okay, so therefore, f of x is discontinuous of the second kind from the right. From the right. So that is the right limit does not exist. Okay. Therefore, f of x is discontinuous of second kind from the right x equal to 0, and it is continuous from the left at x equal to 0. Hence, it's a mixed continuous. Mixed discontinuous at a point x equal to 0. Maybe one side is either right hand side or left hand side is a continuous or first discontinuous of first kind. Another side is discontinuous of second kind. So already we know that what is discontinuous of first kind. So discontinuous of first kind is means both the right hand side limit or left hand side limit exists but not equal. Okay. Second kind is none of the limits exist, but from the right it exists, but the left is not exist. Therefore, we say it's a mixed discontinuous. But anyway, in the question they will ask about the mixed continuous, but just you should know the first three discontinuous. Okay, removable discontinuity, discontinuous of first kind, discontinuous of second kind. Okay, this is enough. So discontinuous of first kind we call as a jump discontinuity. Now, we discuss some more examples. Then, okay. Sin 1 by x function is very important. Okay. Now, similar function we can discuss f of x equal to sin 1 by x. Sin of 1 by x if x is non-zero, and 0 if x equal to 0. Now, what is the right hand limit, left hand limit? Because we have to check at a point x equal to 0. Okay. So, what is the thing? What is the right hand limit? What is the left hand limit? It is exist or not?
Sir, both will be not existing, sir.
Which one? Right hand limit, left hand limit. Anyway, right hand limit does not exist. Okay, we can find out two different sequence xn converges to 0, but a sign of 1 by xn may be sometimes 0, sometimes 1. Therefore, even if we take positive side, again this does not exist. Even if we take less than 0, again that is not does not exist, right? So therefore, this is nothing but discontinuous of second kind. Because discontinuous second kind is nothing but neither the right hand limit nor the left hand limit exist. Even if you take positive side or negative side, if you take 0. Okay. So therefore, this function is a discontinuous of second kind, because even if you find the right hand limit or left hand limit, both the limit is not exist. None of the limit exists, therefore with the discontinuous of second kind. Okay. Therefore, this is discontinuous of second kind, because neither right hand limit nor the left hand limit exist. Okay, now we discuss some more example. So, but this function is not continuous, but just a little bit I change the function. That function is continuous. So, what is the function? Just I am going to multiply x to sin 1 by x. So, that is f of x equal to x into sin of 1 by x, where x is non-zero. 0 if x equal to 0. Now already we know that what is the limit x goes to 0, x into sin 1 by x. Sin 1 by x is bounded function, and this is goes to 0, therefore the product goes to 0. Okay. Now what is 0 actually in the function? It's nothing but f of 0. Because for the point 0, x equal to 0, the value is 0. Therefore, f of 0 is 0. So, limit x goes to 0, f of x equal to f of 0. Therefore, what can you say about f? F is what?
Continue.
F is, yeah, continuous at a point 0. Okay. Similarly, I am taking instead of sin 1 by x, I am taking cos 1 by x. Now, what can you say about the function? F of x equal to x into cos of 1 by x. Again, x is not 0. 0 if x equal to 0. Now, again, what is the limit? X goes to 0, x into cos of 1 by x. Again, cos 1 by x limit also not exist, but if you product some function which goes to 0, then by the theorem this is bounded, cos also bounded to 1, and as x goes to 0, sin x goes to 0, therefore this is nothing but 0. Okay, therefore this is nothing but f of 0, therefore f is continuous at point x equal to 0. Okay, any doubt? Okay, now I will ask some question. Suppose in the function they give some unknown values a, b, c, and for what values of a, b, c, that function is continuous. Anyway, otherwise sometimes they will give is continuous, then find the values of a and b. So what is the function? Determine the constant a and b so that the function defined below is continuous everywhere. Okay, determine the constants a and b. Constants a and b so that the function f defined below, the function f defined below is continuous everywhere. Defined below is continuous everywhere. That is, every point is continuous. Continuous everywhere. So what is the function? F of x equal to two x plus 1 for x is less than or equal to 1, and ax square plus b for the value 1 strictly less than x, strictly less than 3. Another one is 5x plus 2e for x is greater than or equal to 3. Now, this function should be continuous. The values of a and b. So then which point we have to take? So look at, there are three intervals. So this is one interval. So in this interval, this is just a polynomial. 2x plus 1 is a polynomial, therefore it's a continuous. Again, if you look at only this open interval 1, 3, this again is a polynomial, therefore it's continuous. Now for any x greater than 3, this is also a polynomial, therefore it's continuous. Now only points is where, for what are the points we have to check for continuity. So we have to connect these two functions. We have to connect these two curve. Finally, we get continuous. Okay. Now we have to connect. So at which points we have to connect? In the first two interval, we have to check these endpoints. So the endpoints of this one, the starting point of this one. Therefore, we have to check what happened if x equal to 1. Both should be equal, right? So this is one function. I am going to start another function. Therefore, suppose I am going to start another function like this. This is a discontinuous. Okay. Therefore, both the curve at the point, this point may be 1. At the point 1, both the functions should be equal, right? Now after 3, we have, suppose I am drawing some other function, but should be continuous. Therefore, at the point 3, both the function takes the same value at most, right? Now tell me that what you will get. We will get two things. What are things you will get? So therefore, this is a one continuous function. This is another continuous function. If you paste these two functions, we have to paste. Otherwise, we will get a discontinuous, right? So that means what? So the left hand limit of this, and then the right hand limit. Okay, the left hand limit of this function, and then the right hand limit of this should be equal, right? So this goes to this side, and this goes to this side. If both the limit exists and equal, then only the function is continuous, right? Therefore, if x goes to 1, actually you will get 3 that side, and this is equal to substitute x equal to 1. Simply, roughly speaking, substitute x equal to 1. So we get a plus b. We get one equation. Now from the last two, so for x equal to 3, what will get? 9a plus b. This is equal to, and x equal to 3 is 2a plus 15. Now this is nothing but 7a plus b equal to 15. We have another equation, a plus b equal to 3. So just to subtract this, we get 6a equal to 12. Therefore, A equal to 2. Substitute A equal to 2 in this equation, therefore B equal to 1. Therefore, A equal to 2, B equal to 1. Then only the function is continuous everywhere. Got it? Any doubt? Any doubt? Okay, now maybe
No, sir.
I will ask one question. You got to tell me for which point the function is continuous. So only thing you have to check the end points, okay? No need to check all other points. Suppose f is defined by f of x equal to minus x. For the point x should be strictly less than minus 1. And minus 1 less than or equal to x less than or equal to 1, the value is 1. For strictly greater than 1, its value is x. Now, this function is continuous at okay. So if we take all points less than minus 1, this is just a polynomial, therefore is continuous. So only thing is you have to check at this point, minus 1 and then 1. You have to check only these points. It is continuous at minus 1 or not. Minus 1 and then 1. It is, the function is continuous at minus 1 or not. That means what? If substitute x equal to minus 1, this should be equal to this. If substitute x equal to minus 1 here, that should be equal, right? So if substitute x equal to minus 1 here, what will get? Minus minus plus, we get 1. But if this contains, does not contain any x, therefore we get 1. Therefore 1 equal to 1, therefore x equal to minus 1, this function is continuous. But we are not going to substitute, but we have to find the right hand limit of this and the left hand limit of this, and this should be equal. Okay, therefore this function is continuous at x equal to minus 1. What about x equal to 1? Now substitute x equal to 1 here, we get 1. If substitute x equal to 1 here, we get 1. Therefore, this function is continuous at, therefore this is continuous at x equal to minus 1 and x equal to 1. Okay, for all other points also the function is continuous. Okay, so only thing we have to check the end points. That is the important thing. Therefore, this is actually continuous at everywhere. So only thing we have to check is continuous at minus 1 and plus 1 or not. Okay. Now I will ask one more question. Suppose f of x is defined to be e power 1 by x by 1 plus e power 1 by x for all non-zero values x. Okay. For 0 values, we define f of x equal to 0 for x equal to 0. Now, what can you say about f? F is dash at some point. First, you got to guess which point we have to check.
For 0.
Yeah, for x equal to 0, we have to check. Is it continuous or discontinuous? Then what we have to do? We have to find the right hand limit and the left hand limit. Both exist and that should be equal to 0. That is f of 0. F of 0 is 0. So what is the right hand limit? That is limit x goes to 0 plus f of x. What is the value? That is, if you take any sequence xn which is greater than 0 and xn converges to 0, then what can you say about f of xn? If suppose you are getting confusion, you can cancel this e power 1 by x and what you will get. So therefore, you can rewrite this f of x as 1 by 1 plus e power minus 1 by x. Okay, you can take e power 1 by x common from the denominator and then cancel it. We get 1 power 1 plus e power minus 1 by x. Now tell me that if x goes to 0, if xn goes to 0, what can you say about this function? What is f of xn actually? So all the xn's are non-zero, therefore f of xn is equal to 1 by 1 plus e power minus 1 by xn. This converges to where?
1, sir.
Yeah, 1. Because e power minus infinity is 0. Because xn goes to 0, 1 by xn goes to infinity. But here minus 1 by x, therefore e power minus infinity approaches to 0, therefore 1. Okay, good. Therefore, we get that the right hand limit is 1. What about the left hand limit? Limit x goes to 0 minus f of x. That is, if you take any sequence xn which is less than 0, but xn converges to 0, then what happens f of xn? So again, f of xn is nothing but 1 by 1 plus e power minus 1 by xn. This goes to, but xn's are negative. Therefore, minus 1 by xn is positive. That is not e, actually e power infinity. So e power infinity. Then this goes to what? E power infinity goes to infinity. So therefore, this goes to 0 because 1 by infinity is 0. Right? Therefore, the left hand limit is 0. Since the right hand limit, left hand limit exists, but not equal. Anyway, this is discontinuous. Got it? Discontinuous at a point x equal to 0. And what type of discontinuity is this? It's a first kind. Right hand limit, left hand limit exist, but not equal. Okay, okay, good. Okay, there are so many examples are there. You got to work with the same thing. Okay. Now we move to that another thing. So far any doubt? Now I hope you get idea for that problem. Yesterday you gave me one problem, right? Now I hope you solved that one. Now you just try it. You will get one limit, but you will not get another limit. So that is one side limit exists, another side limit does not exist. You just to try it. Okay. Now next we discuss this limits concept. The syllabus contains uniform continuity, I think so. So when we say a function is uniformly continuous, so we know the definition of continuous. Okay. Now we state the definition of uniform continuous. This is very important definition. So next one is uniform continuity. Uniform continuity. So we can talk about uniformly continuity on a set, but we can discuss. We can talk about the continuity at a point as well as continuity on a set. But uniformly continuity we can talk about only on set, not for points. Okay, so that is uniform. That is so uniform means what? It's uniform to all the students in the school or college. Okay, we cannot talk about the uniform in particular student. Okay, so uniform of that college or the school. Okay? Therefore, uniform continuity is what? It's a continuity on the entire set. Now, definition. Suppose we have a subset. Let J is a subset of R, and we have a function. A function f from J to R is said to be uniformly continuous. Is uniformly continuous on J. Uniformly continuous on J if for every epsilon greater than 0 there exists a delta greater than 0. This delta depends only on this epsilon, okay, such that if you take any points, any 2 points x1, x2 in J with the distance between x1 comma x2 is less than delta, implies modulus of f of x1 minus f of x2 is less than epsilon. So this delta depends only on epsilon. So it's a function of epsilon only, not a points, this x1, x2. Okay, but continuity means what? This delta depends on some other points also. Okay, then we say it's a continuity. Now the theorem says every continuous function is every uniformly continuous, but continuous may not be uniformly continuous. We will discuss some example and theorem. We can just characterize that uniformity of some function. Okay. So the theorem, the first theorem is every uniformly continuous function is continuous function on the interval. Okay. So every uniformly continuous function is a continuous function. But converse need not be true. Not all the continuous functions are uniformly continuous function. Okay, but the converse not true. In general, the converse need not be true. Okay, why? We discuss some example. So we had discussed some uniformly continuity of a function. So example, f is a function from open interval 0 comma infinity to r defined by f of x equal to 1 by x, because x is positive, therefore we can define 1 by x. Okay. Now we can talk about the uniformly continuity of this one. So, but if we take alpha comma infinity where alpha is positive, if alpha is positive, then if you consider this interval alpha comma infinity, then the function is uniformly continuous on this interval. Okay. But in this interval 0 comma infinity, this function is not uniformly continuous. Okay. So I will give some theorem so that we can easily prove that this function is not uniformly continuous. So there is some special property is there for uniformly continuity. What is the special in that? If you give any Cauchy sequence, suppose the function is uniformly continuous, if you give any Cauchy sequence in the domain, it takes to the Cauchy sequence. That is a very important property of this uniformly continuous. So I state the theorem. Suppose a function is uniformly continuous, then suppose let f is a function from j to r, j is any subset of r, is supposed to be uniformly continuous. Uniformly continuous. Then f maps Cauchy sequence in j to Cauchy sequence in r. Then f maps or maps Cauchy sequence. Take any Cauchy sequence in j. Cauchy sequence in j is maps to Cauchy sequence in r. It's very, very important theorem. To check the function is uniformly continuous or not, suppose we have to assume that the function is uniformly continuous, then by this theorem, every Cauchy sequence maps to Cauchy sequence. So Cauchy sequence means we know that, but in the real case, every Cauchy sequence is nothing but convergence sequence. All the convergence sequence are Cauchy sequence, all the Cauchy sequence are converges. Okay, in R. Now, if we take this example now, okay, so I'm going to take some Cauchy sequence here, xn. So what is the, can you give any Cauchy sequence? So actually give any convergence sequence here. Any convergence sequence is a Cauchy sequence, okay? Now give some convergence sequence in this positive real axis.
1
Should,
minus 1 by n.
yeah, okay, but why you take so complement? Simply take 1 by n. 1 by n is all positive. Therefore, 1 by x is a sequence in here. Since it converges in real numbers, therefore it is Cauchy. Therefore, it is Cauchy in this interval. Okay, and therefore this is Cauchy sequence. Cauchy in this interval 0, infinity. Suppose we assume that f is uniformly continuous, then f of xn should be Cauchy. But what is f of xn? Xn is 1 by n. 1 by 1 by n is nothing but n. But n is not Cauchy. Why n is not Cauchy? If it is Cauchy, it should be converges. But n, this is a divergence sequence 1, 2, 3, 4, and so on, right? Therefore, we get a contradiction to this theorem. Therefore, this f of x equal to open 0, infinity to r, f of x equal to 1 by x is not uniformly continuous. Is not uniformly continuous. But if we take the domain is this, alpha comma infinity, but alpha is positive number but not equal to 0, then the function 1 by x is uniformly continuous. Why? Now we can use the epsilon delta definition. We can find that source delta is so. Suppose f is a function from alpha comma infinity to r, where alpha is a non-zero number, okay, positive number, defined by f of x equal to 1 by x. Now estimate what is f of x, f of y. So by the definition of f, this is nothing but 1 by x minus 1 by y. If you simplify this, you'll get y minus x by x into y. So this is nothing but 1 by mod xy into modulus of y minus x. We can write x minus y. We can take minus outside, we can write this. Since both the x and y are in this interval, right? So x comma y is in alpha comma infinity. That means what? Both the x and y should be bigger than alpha. So alpha is strictly less than x, therefore 1 by x is strictly less than 1 by alpha. Again, alpha is strictly less than y, therefore 1 by y is strictly less than 1 by alpha. Therefore 1 by x is less than 1 by alpha, therefore we get this is less than 1 by alpha square times modulus of x minus y. Now we can choose delta. So epsilon is given, epsilon greater than 0 is given. Okay. Choose delta is, okay, epsilon by alpha square. So now whenever mod x minus a is less than delta, so therefore this quantity is less than delta. But delta is epsilon by, okay, sorry, then, then you have to take alpha square. Then alpha square cancel, we get less than epsilon. So therefore modulus of x minus epsilon less than epsilon. Now this delta depends only on epsilon and some constant alpha square. Alpha square is just a constant, but it's not depends on the points x and y. Therefore, is uniformly continuous. If the delta depends only on the epsilon and some constant, then such a continuous function is uniformly continuous. That's why this function is uniformly continuous. If you take alpha is greater than 0. If alpha equal to 0, the function is not uniformly because if it is uniformly, take Cauchy sequence takes to Cauchy sequence, but this is not thing. It's one of the important theorem in the uniformly continuous. Next, another important thing. So when a continuous function is uniformly continuous, that is another important thing. Maybe state as a theorem. Suppose the domain of the function is bounded and closed, then any continuous function is uniformly continuous. Okay, let J be a closed and bounded set. Be a closed and bounded subset of R. Closed and bounded interval. Then any continuous function, defined on J is uniformly continuous. Any continuous function f defined on J to R is uniformly continuous. So a continuous function defined on the closed and bounded subset of R then is to be uniformly continuous. Very, very important theorem. Okay. So first you got to look at the domain of the function. Okay. First you got to check that the function is continuous or not, because every uniformly should be continuous, right? So first you got to check the function is continuous or not. If it is continuous, next you have to look at the domain of the function. If the domain is closed and bounded, then you can directly say this is uniformly continuous. No need to check the models of f of x minus f of y, all the things. Okay. First you got to look at the function. If it is continuous, then look at the domain of the function. If it is closed and bounded, then automatically this is uniformly continuous. Suppose you remove at either closed or bounded in the domain, that may not be uniformly continuous. Okay. That's a very important thing. Okay. So, maybe we have some more theorem. Okay, there are a lot of theorems there to check a function is uniformly continuous or not. But the one important consequence characterization of Cauchy theorem that is also very important theorem. So the theorem says when the function is uniformly continuous. So a function from R to R, a function f from R to R is uniformly continuous. Is uniformly continuous if and only if you take any two sequences, whenever x and yn is a sequence, the difference whenever xn and yn are two sequences are sequence such that the difference xn minus yn converges to 0 are sequences of R are sequences of the real number R such that the modulus of xn minus yn, this sequence, if it is converges to 0, then we have modulus of f of xn minus f of yn converges to 0. And this is happened, then the function is uniformly continuous on R. Okay, whenever if we take any two sequence, maybe the sequence need not be converges, but the subtraction of two sequence converges 0, then the subtraction of the image of the sequence also converges 0, then the function is uniformly continuous. Okay, it's very, very important thing. Okay. Now maybe I will ask some problem based on these theorems. This is also very important thing. Okay, now example. First one is f of x equal to sine 1 by x. Sine of 1 by x. Defined on the interval open interval 0, 1. Check this function is continuous or not on this interval 0 to 1. So sine of 1 by x is continuous function, okay, but the domain is open interval 0, 1. It's a bounded set but not closed set. So suppose the function defined on the endpoint. So only problem is these two endpoints. Okay. Suppose the function f defined on these two endpoints, then this become a closed interval 0, 1. This is a closed and bounded. This is a continuous. Therefore, by theorem is uniformly continuous. Okay. But anyway, we can define for these endpoints. For x equal to 1, it will not create any problem, because if substitute x equal to 1, we get sine 1. It's a well-defined function. But if we take x equal to 0, the limit does not exist, right? Therefore, we cannot extend this function to this interval. Okay. So there is a theorem. The theorem says, suppose a continuous function defined on some open interval a comma b. Okay, suppose simply I'm saying suppose f is some continuous function defined on the open interval a comma b, and suppose it is possible to extend this function to these endpoints, two endpoints, that is with the limit x goes to a minus f of x exists, and then the left hand limit of this exists, limit x goes to b plus f of x exists, then we can extend this function to these two endpoints. Therefore, we get a new function g that is continuous on this closed interval a comma b. Since this is a closed and bounded and continuous, therefore this f is uniformly continuous. Therefore, we say f is uniformly continuous. Okay. So the theorem says if it is possible to extend a continuous function defined on open interval a comma b to these endpoints, two endpoints, okay, and this, the limit exists, then definitely f should be uniformly continuous. Okay. Anyway, we can extend this function to this endpoint. Only one endpoint, namely 1. But we are not extend this function to this point because the limit x goes to 0 plus sine 1 by x not exist. That's why we are not extend this function to this interval. Anyway, now how to check this function is uniformly continuous? Use any theorem. Suppose uniformly continuous, then what is the contradiction you will get? So first thing is you got to think about the Cauchy sequence. Okay. So every Cauchy sequence takes to Cauchy sequence, right? So can you do any Cauchy sequence here? Xn is 1 by n. It's a Cauchy sequence. Suppose if it is uniformly, then f of xn also Cauchy sequence. So what is f of xn? Is sine of 1 by n, 1 by n is nothing but sine n. Already we know that sine n is divergent sequence. Therefore, is not a Cauchy sequence. Any divergent sequence is not Cauchy. Therefore, this is not uniformly. Is not uniformly continuous on this interval 0 to 1. Got it? Now, now tell me that. Now the second question. Suppose I am multiplying with the x. It is g of x equal to x into sine of 1 by x is defined for all points in the open 0 close to 1. Is it uniformly continuous or not? So now we got to check only the points 0. If it is possible to extend this function to this close to 0 comma 1 and that function is continuous, then that should be uniformly continuous. That means what? We have to check the function limit exists at the point or not. That is the left hand limit. Sorry, the right hand limit. Okay. So there is 0. It is 1. If we take some x here and this x approaches to this side, then if the limit exists, then we can extend this function to close to 0 comma 1. So that's what we have to check. Limit x goes to 0 plus g of x. It is exist or not? Because if it is suppose it is here, we can look at this direction also, but this is same as actually limit x goes to 0. Okay, now what is the value of this? Again, this is a bounded function and this goes to 0, therefore this goes to 0. Now we can extend the function. This now we define a function, new function. Okay, so what is the new function? F of x? F of x equal to g of x for all points in this interval 0 to 1. For the only point x equal to 0, I am defining the limit. What is the limit? 0. Now, what is the limit? X goes to 0, f of x is nothing but f of 0. F of 0 is 0 actually. So, this f is continuous on the entire closed interval. And this is uniformly continuous. Therefore, g is uniformly continuous. The given function is uniformly continuous. This is uniformly continuous. So any doubt in this? So idea is suppose a function, a continuous function defined some interval But suppose they missed one interval, either one side or another side. It is possible to extend the given continuous function to the closed interval a comma b. That extension function also continues. If it is continuous, then the given function is uniformly continuous. If it is possible to extend the endpoints, but in the previous this previous problem, it is not. It's very difficult to extend. Anyway, we can say that using the theorem, if it is uniformly continuous, this in particular this 1 by n Cauchy sequence, but f of xn is not Cauchy. Or even you can try to extend this continuous this function to these two endpoints. We can extend to this one because limit exists. So limit x goes to 1, f of x, this limit exists actually 1 minus, because we have a interval. Okay, so this limit exists, but this limit limit x goes to 0 f of x not exist. We cannot extend that function to these endpoints. One endpoints we can extend to one endpoint, but we cannot extend to this other endpoint. If it is possible to extend and it is continuous, then it is uniformly continuous. Okay. So there are a lot of theorems are there. So these are all important theorems to check a function is uniformly continuous or not. Okay. So this theorem is very important. If you take any two sequence x and y n, if subtraction converges to 0, then the image of x and y n also converges to 0, then such a function is uniformly continuous. Or the continuous function domain is closed and bounded, then we can say it's a uniformly continuous. And if it is uniformly continuous, it takes Cauchy sequence to Cauchy sequence. So these are all important theorems to check uniformity. Okay. So just try to solve some other problems related to this uniformly continuous. If you have any doubt, you can ask me. Okay. Now I can stop now. Thank you.